Hey guys, welcome to this easy maths video on the Fundamental Theorem of Calculus. In this video we'll be exploring the two theorems which relate to the Fundamental Theorem of Calculus, being the Fundamental Theorem of Calculus Part 1 and Part 2. We will then look at the proofs for each of these theorems and examples where both of these theorems are applied. So the Fundamental Theorem of Calculus is an extremely powerful theorem which explains the relationship between differentiation and integration, being the two main topics within calculus. So the first theorem is the Fundamental Theorem of Calculus Part 1, and the theorem states, let lowercase f be a continuous function on the closed interval from a to b, and the function uppercase f is defined as f of x equals the integral from a to x of lowercase f of t, and we're integrating that with respect to t. Now an uppercase f is also continuous on that same closed interval from a to b and is differentiable on the open interval from a to b. Where uppercase f has the following derivative, if we take the derivative of uppercase f, we end up getting lowercase f of x. Okay, so the way we can think about this function uppercase f is that it's the function which represents the area under the curve between 2 points a and x. So we know when we're taking the integral of a function between two limits, we are essentially taking the area under the curve between 2 points. And that's exactly what we've got here. We've got our t-axis here and our f of t-axis here. And the area of the function is between a and x, and that whole area is represented by uppercase f of x. So now we are going to try and prove this theorem using the definition of uppercase f of x. We're going to show that when we take the derivative of uppercase f of x, it gives us lowercase f of x. Okay, so in order to prove the Fundamental Theorem of Calculus Part 1, we are told in the theorem that uppercase f is differentiable. So in that case, we can use the definition of the derivative, being the definition of the derivative from first principles, to show what the derivative of uppercase f of x should be. The derivative of uppercase f of x is uppercase f dash x equals the limit as h tends to 0 of uppercase f of x plus h minus uppercase f of x all over h. Okay, so that's the definition from first principles. So in order to work out what this limit is on the right hand side, we're going to need to break up this fraction. So if we look at the numerator first, which is this bit, we can write out the numerator by using the definition of uppercase f of x. So uppercase f of x plus h minus uppercase f of x equals, so for uppercase f of x plus h, we can use the definition of uppercase f, but instead of integrating from a to x, we're going to be integrating from a to x plus h. So the integral from a to x plus h of f of t integrating with respect to t, and then we can just subtract the definition of f, which is the integral from a to x of f of t integrating with respect to t. Okay, so we can make the assumption that x plus h is going to be greater than x. Okay, so what that means is we could split this integral, the integral from a to x plus h of f of t with respect to t, into two separate integrals. So first we can integrate from a to x of f of t with respect to t, and then we can add the integral from x to x plus h of f of t with respect to t, and then we can subtract the integral from a to x of f of t with respect to t. So now you can see that these two integrals will cancel each other out, and we're left with the integral from x to x plus h of f of t with respect to t. Okay, so we saw that we were able to simplify the numerator for the definition of the derivative of uppercase f of x. Now, what we're going to need to do is we're going to need to come up with two different estimates for the area underneath the curve. And the way we're going to do this is we're going to use a lower bound and an upper bound. So we're going to take the lower bound for the area by splitting the curve up into a series of rectangles from a to x plus h in this case. So this is for the function uppercase f of x plus h. So we can represent the integral between a and x plus h as a series of rectangles below the curve where the total area is a lower bound for uppercase f of x plus h. Okay, so as we can see, this area is going to be slightly smaller than the actual area from a to x plus h. And we can also come up with an estimate for the upper bound, which will be the area between a and x plus h as a series of rectangles above the curve, where the total area is an upper bound for uppercase f of x plus h. Therefore, we can see that this estimate will be slightly greater than the actual estimate from a to x plus h. Now, and as we saw in the proof, we're only interested in the integral from x to x plus h, and that was taking the function of uppercase f of x plus h minus uppercase f of x. Okay, so in that case, this means we only need to consider the area of the rectangles between x and x plus h that are below and above the curve. So this is just one rectangle. So below the curve, for the area of our lower bound, we've got this rectangle between x and x plus h, and in order to work out its area, we're just going to take the base of this rectangle and multiply it by its height. So its base is going to be this distance here from x to x plus h, which is h, and then the height of this rectangle, which happens to be the height of this function at a value of x. So that is f of x. So the area for the lower bound will be h times f of x, being lowercase f of x. And then we can do the exact same thing for the upper bound. So we've got this rectangle between x and x plus h. So again, this is going to have a base of h. And then the height of this rectangle, well, the height of the rectangle is equal to the function at a value of x plus h. So it's going to be h times lowercase f of x plus h. So therefore, we end up with this as our following result. We have the integral of x to x plus h of lowercase f of t with respect to t between h of lowercase f of x and h of lowercase f of x plus h. So now we have a lower bound and an upper bound for this integral. We can say that this integral is h of lowercase f of x, which is between the integral of x to x plus h for lowercase f of t with respect to t. And then we've got an upper bound of h lowercase f of x plus h. Then what we can do is we can divide this inequality through by h. So we're going to get lowercase f of x is less than or equal to 1 over h of the integral of x to x plus h of lowercase f of t integrating with respect to t, which is less than or equal to lowercase f of x plus h. Now, this integral here, we showed previously, is equal to uppercase f of x plus h minus uppercase f of x. So we can just write this inequality as lowercase f of x is less than or equal to uppercase f of x plus h minus uppercase f of x all over h, which is less than or equal to lowercase f of x plus h. So now what you should be able to see is what we've got in the middle is very similar to the definition of the derivative from first principles. The only thing it's missing is the limit as h tends to 0. So what we can do is we can take the limit as h tends to 0 for this whole inequality. So as h tends to 0 for lowercase f of x, we're also going to have the limit as h tends to 0 of uppercase f of x plus h minus uppercase f of x all over h, and this is going to be less than or equal to the limit as h tends to 0 of lowercase f of x plus h. Now all we have to do is evaluate the limit. So the limit as h tends to 0 of f of x is just f of x, since f of x doesn't depend on h. Now we can't simplify this limit in the middle, however we know that this is the definition of the derivative for uppercase f of x. The limit on the right hand side, so the limit as h tends to 0 of lowercase f of x plus h, will just become lowercase f of x. And now what you will notice is that our inequality has the same lower and upper bounds, which means that it's not an inequality anymore, we have an equation. So we've got the limit as h tends to 0 of uppercase f of x plus h minus uppercase f of x divided by h equals lowercase f of x. And of course, this whole result on the left-hand side is the definition of the derivative for uppercase f of x from first principles. So we've just got uppercase f dash x equals lowercase f of x. And this is the result from the Fundamental Theorem of Calculus, Part 1. So this was the result from the Fundamental Theorem of Calculus, Part 1, and it said that the derivative of uppercase f of x is equal to lowercase f of x. So what does this actually mean? This means that uppercase f is the antiderivative of lowercase f. So if we take the integral of lowercase f of x, we will end up with uppercase f of x. So that's what we mean by the term antiderivative. So now we move on to the second theorem, which is the Fundamental Theorem of Calculus Part 2. So this theorem states, let lowercase f be a continuous function on the closed interval from a to b, and if g is any antiderivative of lowercase f, then the integral from a to b of lowercase f of t, integrating with respect to t, is equal to g of b minus g of a. What does this theorem actually mean? We can essentially think of g of b minus g of a as the difference between the two areas g of b and g of a. So if we remember previously, the antiderivative can be thought as a function for the area under a curve between 2 points. So uppercase g of a is the area function between the 2 points 0 and a. And then g of b will be the area function between 0 and b. So when we subtract g of a, we will end up with the area g of b minus g of a. And that's exactly what we've got here. We can represent that as an integral of lowercase f of t between the two limits a and b. So now we're going to look at the proof for the Fundamental Theorem of Calculus Part 2. So if we remember, we are proving that the integral between a and b of lowercase f of t integrating with respect to t equals the antiderivative g, so g of b minus g of a. So we know that uppercase f is the antiderivative of lowercase f. And in order to prove this theorem, we're going to introduce another antiderivative g. So suppose g is another antiderivative. So remember, we can think of antiderivatives as area functions. They represent the area under a curve between 2 points. So if we took the antiderivative f minus the antiderivative g, this would be equal to some constant c. Okay, so where c is a constant. Now, from the Fundamental Theorem of Calculus, part 1, we know that the antiderivative of f is equal to the integral between a and x of lowercase f of t integrating with respect to t. So if we replace x with a, so the antiderivative of f of a will be equal to the integral from a to a of lowercase f of t integrating with respect to t. Well, this will just end up being 0. There is an area of 0 when we are integrating from a to a. Okay, so from here we can conclude that the antiderivative of f at a is equal to 0. So when we take the antiderivative of f of a minus g of a, then essentially this should also be equal to some constant c, right? Because we're taking one area, f of a, and subtracting it from another area, g of a. So we end up with some constant c. But of course now we know that f of a is equal to 0. So this implies that c is equal to minus g of a. So now we can actually go back to this first statement that we made up here. When we take the difference between two antiderivatives f and g, we end up with some constant c, and that was at a point x. So if c equals minus g of a, we're going to get f of x minus g of x equals minus g of a. Now, if we look at the theorem, we need to prove that the left-hand side, so the integral from a to b of lowercase f of t integrating with respect to t equals the difference between g of b and g of a. So we need to think, how are we going to get to this result here? Well, essentially this is equal to the antiderivative f where x is equal to b. Okay, because if we remember from the Fundamental Theorem of Calculus part 1, this is what the theorem states, what I'm highlighting here. And if we substitute in b for x, we will end up with the integral from a to b of lowercase f of t integrating with respect to t. That is exactly equal to the left-hand side of this equation. So if we say let x equal b, then uppercase f of b minus g of b equals negative g of a. Okay, and if we now add g of b to both sides, we get f of b is equal to g of b minus g of a. And f of b is equal to the integral from a to b of lowercase f of t integrating with respect to t. So therefore, the integral from a to b of lowercase f of t integrating with respect to t is equal to g of b minus g of a. And therefore we have shown the result for the Fundamental Theorem of Calculus Part 2. So now we're going to look at some examples of applying the two theorems, Fundamental Theorem of Calculus Part 1 and Part 2, to a few examples. So the first example we will have is uppercase f of x equals the integral from 4 to x of the square root of t cubed plus 5, and obviously we're integrating with respect to t. So we want to find the derivative of uppercase f of x. So the way we're going to do this, first we're going to use the Fundamental Theorem of Calculus part 1. What that says is if we've got some function uppercase f of x, then that is equal to the integral from some constant a to an upper limit of x, and we're integrating the function lowercase f of t with respect to t. And from this result, when we take the derivative of uppercase f of x, we will get lowercase f of x. Now this integral is fairly similar. We've got some function of t here, and we're integrating with respect to t, but the difference is that we've got a constant 4 for our upper limit, and then our x value down here is our lower limit. Whereas the Fundamental Theorem of Calculus says that our x value should be our upper limit. So essentially what we're going to have to do is we're going to have to rewrite this integral. And remember, if I've got some function, so if I draw this function, where this is my t-axis, this is my f of t-axis, I don't really care what the function looks like. Let's say it looks something like this, and we've got a value of x here, because the integral shows that x is smaller than 4, and then we've got a value of 4 here. So what we could do is we could take the integral from 0 to 4, which would cover this whole region here, and then we could subtract the integral from 0 to x, which would take away this region here, and then we're just left with the yellow region from x to 4. So that's essentially what we're going to do with this integral. So we can say that uppercase f of x is equal to the integral from 0 to 4 of the square root of t cubed plus 5, and we're integrating with respect to t, minus the integral from 0 to x of the square root of t cubed plus 5, and again we're integrating this with respect to t. Okay, so we have this first integral. Now, rather than trying to integrate it, we will just say that this function is lowercase f of t, and we can say the same for this integral here. Okay, so what that means is when we take the integral of this function, we're going to end up with the antiderivative uppercase f of t. Because this is what the Fundamental Theorem of Calculus states. It states that the function uppercase f is the antiderivative of lowercase f. And this result has limits t equals 0 and t equals 4. And then we're going to subtract the antiderivative uppercase f of t, but this time we've got limits of t equals 0 and t equals x. So now what we're going to do is we're going to plug in these limit values into the antiderivative and essentially work out their difference. And this is using the Fundamental Theorem of Calculus part 2. If we remember that if we take the integral from a to b of lowercase f of t with respect to t, this is equal to some antiderivative g, so the antiderivative of g of b minus g of a. Okay, and this is essentially just the difference between two areas under a curve. So if we apply the Fundamental Theorem of Calculus part 2, we will end up with uppercase f of 4 minus uppercase f of 0 minus, so we're going to have this in brackets, uppercase f of x minus uppercase f of 0. And then if we expand the brackets, so we're still going to have this result, and then we're going to have minus uppercase f of x, and then this is going to be plus f of 0. What you will notice is that these two results cancel each other out. And now we're left with the antiderivative f of x is equal to this result here. So now we can just take the derivative of uppercase f of x. Now, uppercase f of 4 is just a constant, and when we take the derivative of any constant, we get 0. So this is 0, and then the derivative of minus uppercase f of x is minus uppercase f dash x. So this implies that f dash x is equal to minus f dash x. But now what we can do is, because we've been applying the fundamental theorems of calculus to the right-hand side of this equation, we know that uppercase f dash x is equal to lowercase f of x by the fundamental theorem of calculus part 1. So this means that uppercase f dash x is equal to minus lowercase f of x. And of course, function t is this result here, square root of t cubed plus 5. So all we have to do is say that uppercase f dash x is equal to the negative square root of not t cubed, but x cubed plus 5. Okay, so that is the derivative for the first question. Now, the second question says that uppercase f of x is equal to the integral from x to x squared of e to the minus t squared, and integrating that with respect to t. So again, this is our function of t, and we're going to use the fundamental theorem of calculus part 1 to differentiate this function. So remember, uppercase f of x needs to be equal to the integral from a to x of lowercase f of t with respect to t, where the derivative of uppercase f of x equals lowercase f of x. Right, so that's what the fundamental theorem of calculus part 1 states. But if we look at this example, we haven't got a constant for our lower limit. Instead, we've got x. So again, we're going to have to use this idea of splitting up the integral. So we can rewrite this integral as the integral from 0 to x squared of e to the power of minus t squared. And we're integrating that with respect to t, and then we're subtracting the integral from 0 to x of e to the power minus t squared. And again, we're integrating this with respect to t. Okay, it's a very similar concept to what we used in the previous example. The integral of lower f is the antiderivative uppercase f. Okay, so that's equal to uppercase f of t, and our limits are t equals x squared and t equals 0, and we're subtracting again the antiderivative uppercase f of t, and our limits are t equals x and t equals 0. Again, I can give both of these functions the exact same antiderivative uppercase f of t because they are the same function. So now we can evaluate these integrals using the fundamental theorem of calculus part 2. So remember that this is the integral from a to b of lowercase f of t, and we're integrating with respect to t. And this is equal to some antiderivative g evaluated at b minus g evaluated at a. So if we apply this theorem, we're going to get uppercase f of x squared minus uppercase f of 0, subtract uppercase f of x minus f of 0. Then if we write this out again and expand this bracket, we are left with this, and the two f of zeros cancel each other out. And now we're left with our antiderivative uppercase f of x is equal to uppercase f of x squared minus uppercase f of x. And now we just need to take the derivative of this function. So the derivative of this function, so this first function, uppercase f of x squared, we can use a chain rule. So we're going to take the derivative of the inside function, which is x squared, so the derivative of x squared is 2x, so we can bring that to the front. Then we're going to take the derivative of this whole function, so that's f of x squared, which is just f dash x squared. And then we're going to take the derivative of minus uppercase f of x, which is minus uppercase f dash x. And now what we can do is we can use the fundamental theorem of calculus to rewrite this derivative as lowercase f of x squared minus lowercase f of x. And then we can use the function f of t. So if we remember, f of t is equal to e to the power minus t squared. And then we can just substitute in x squared and x. So we're going to get that this is equal to 2x e to the power of minus x to the power 4. And then this is minus e to the minus x squared. And that is the derivative for uppercase f for this question.